Good afternoon, students. Today we will continue the previous video. In the previous lecture, I have already discussed about the partial derivative of two variables x and y. I just recall the definitions of partial derivative. That is, partial derivative of x. That nothing is what derivative of f with respect to x, keeping y is constant. Similarly, when you are going to take the partial derivative of y, you have to take x as constant. Now today we will have to discuss the functions of several variables, that is more than two variable functions are occurring. So as we have seen, a function of two variables f of xy has two partial derivatives, del f del x, del f del y. In an exactly analogous way, a function of three variables f of x, y, u has three partial derivatives, namely del f del x, del f del y, and del f del u, and so on for functions of more than three variables, each particular for more than three variables. Now, what is the partial derivative of f function of x, y, u, v, w, and so on? So, for a function of several variables, that is z equal to f of x, y, u, v, w, and so on, the partial derivative of f with respect to v, say, is denoted by del f del v, and is obtained by differentiating f of the function, the respective function, with respect to v in the usual way by treating all the other variables as constant. That is, similarly, if you are going to find out the partial derivative f with respect to x, in that case you have to take the other variables, that is u, v, w, y, you have to take constant. So alternative notations for del f del v when z equal to function of x, y, u, v, w are f suffix v x, y, u, v, w and f v, or you can simply write del z del v. One example is given here. There is two examples. You have to find del f del x as well as del f del u for the function f of x, y, u, v, that is function of four variables, equal to x square plus xy square plus y square u cube minus 7 u v to the power 4. So for finding del f del x, you have to keep y u v as constant. So del x of x square is twice x. So y square is constant coming also. Del x of x is 1. So y and u you have to take constant. So this should be 0. Similarly, u and v is also 0. So the result is del f del x equal to twice x plus y square. See here. Then what is del f del u? Del f del u means what? Partial derivative of f with respect to u, keeping x, y, and v are constant. So del f del u equal to, suppose del u of x square is 0, because with respect to u is also occurring. So similarly, x, y square is also 0. Del u of y square is a constant coming outside. U cube is equal to thrice u square minus 7 v to the power 4. That is, the result is 3u square y square minus 7 v to the power 4. So one physical aspect for partial derivative is that if we consider the pressure P for 1 mole of an ideal gas is related to its absolute temperature T, capital T, and specific volume small v by the equation PV equal to RT. It is a well-known expression from chemistry where R is the gas constant. Obtain simple expression for the coefficient of thermal expansion, that is alpha, which is defined by alpha equal to 1 by v del v del P at the point capital P, at pressure P. And also you have to calculate the isothermal compressibility, capital kappa T, which is defined by kappa T equal to 1 by minus 1 by v into del v del P at capital P. So for finding the thermal expansion alpha, that is given by 1 by v del p at the point pressure. So first you have to find v in terms of p, that is see here v equal to RT by p. So clearly del v by del t is what R by p at the point p. So alpha equal to 1 by nu 1 by p del v by del t of p equal to R PV, that is equal to 1 by t. R PV is 1 by t. Yes. So this is the expression for the coefficient of thermal expansion. Similarly, for finding the isothermal compressibility, you have to express the well-known equation PV equal to RT as P in terms of P. So P equal to RT by P. So del V del P equal to minus RT by P square. R by P minus RT by P square. So kappa T equal to minus 1 by P del V by del P at the point T equal to RT by P square equal to 1 by P. So these are the two expressions, that is the two applications for partial order derivatives. So few examples, exercise problems are here. Already the answers are given by here. So the students are asked to find the solutions of other questions also. Next we will move to the second part of partial derivative, that is second order partial derivatives. So what you have to do here we have to perform two successive partial differentiation of a function f of xy with respect to x holding y constant, which is denoted by del square f by del x square, or simply f xx with within bracket xy, and is defined by del square f del x square equal to del x of del x. So for a function of two or more variables, as well as del square f del x square, other second order partial derivatives can be obtained. So most obvious is the second derivative of f of xy with respect to y is denoted by del square f del y square, or simply f of y, which is defined as del square f del y square equal to del y of del f del y. So clearly an example is done over here, two examples actually. So example 5 is what you have to find del square of del x square and del square of del y square for f of xy equal to x cube plus x square y square plus 2y cube plus 2x plus 1. So what you have to do, first thing is what you have to find del f del x. So del f del x is what with respect to y is y is regarded as constant. So del f del x equal to 3x square plus twice xy square plus 2. Okay, so now del square of del x square is what del x of del f del x. So del x of already del f del x is find out as 3x square plus 2xy square plus 2. So what is the partial derivative of this expression with respect to x is what 6x plus 2y square. This is the expression. Then similarly you will find the partial derivative of f with respect to y. What is that? Twice yx square plus 6y square plus 1. So x is regarded as constant. So similarly, if you are going to find del square f del y square, that is equal to del y of del f del y. So del y of what is del f del y? Here are 2x square y plus 6y square plus 1. So again take the partial derivative of this function with respect to y. So what is that? Twice x square plus 12y. This is the solution. So you can we can use the other alternative notations when evaluating these derivatives. So find f of xx, that is del square f by del x square at the point minus 1 and 1, and f of yy, that is del square f del y square at the point 2 and minus 2. For f of xy is x cube plus x square y square plus 2y cube plus twice x plus y. This problem is similar to the previous one, but just the difference is In this case, you have to find both the second order partial derivative at some particular points. So clearly already we have find out del f del x, del square of del x square, that is 6x plus 2y square. So del square of del x square at the point minus 1 is what? You have to replace x by 1 and what? X by minus 1 and y by 1 to get the value is minus 4. Similarly, second order partial derivative fyy at the point 2 and minus 2 will be replace x by 2 and y by minus 2 will be minus 60. So next we will move to the next section of partial order derivative, that is mixed second derivatives. So in this section, what is it is the possible to carry out a partial differentiation of f of xy with respect to x, followed by partial differentiation with respect to y, or vice versa. That is, the results are examples of mixed derivatives. We must be careful with the notations here. We use del square of del x del y is what to mean differentiate first with respect to y and then with respect to x, and we use del square of del y del x to mean differentiate first with respect to x and then with respect to y. So the two expressions for mixed second order derivatives is given here. That is del square of del x square equal to so del square f by del del x del y, which is equal to del x of del f del y, and del square f by del y del x equal to del y of del f del x. So a simple example is given over here. For f of xy equal to x cube plus 2x square y square plus y. So you have to obtain del square f del x del y. So del square f del x del y is can be written as del x of del f del y. So del f del y is what? 4yx square plus 4y square. Sorry, 3y square. So del square f del x del y is what? Del x of 4x square plus 3y square, so 8xy. Okay, so it's very simple. The remaining possibility is to differentiate first with respect to x and then with respect to y. That is del y by del y of del f del x. Okay, now for the function in example 7, del f del x equal to 3x square plus 4xy square, and del square f del y del x equal to 8xy. So from here it is clearly noticed that for the given function, del square f by del x del y is equal to del square f by del y by del x. Okay, so from these things we can conclude one thing, that this equality of mixed derivative is true for all functions which you will likely to meet in your studies. To evaluate a mixed derivative, we can use the alternative notation. To evaluate del square f del x del y, we write f of yx with respect to x and y, and to indicate the first differentiation is with respect to y. Similarly, del square f del y del x is also denoted by f of x by x comma y. So in example 8, it is asked to find f of yx at the point 1, 2. The given function is f of x is there. So f of x, that is partial derivative with respect to x, is for 3x square plus 6xy. 4xy square. So f of yx is what? F of yx is what? 4x square y plus 3y square. Clearly, we can put the values to get the value of f of x as f of yy, f of xy, as well as f of x and f of yx. So today we will stop at this part. So next day we will start a basic engineering problem regarding the partial order derivatives. So thank you.